Yeah, Dr. Birdi, we are going live.
Okay.
A very good afternoon to one and all present. Myself, Dr. Kiranjeet, and on behalf of Prevented Team, I welcome all of you who have joined us for the webinar entitled Use of Botanicals for Combating Antibiotic Resistance Pathogens. This initiative is part of the Prevented project, which is entitled as Risk Management and Prevention of Antibiotic Resistance, which is co-funded by Erasmus Plus program. As part of this project, this is our 7th webinar, and the key aim of this project is to create awareness on antibiotic resistance, which can be the upcoming pandemic. So before going into the technical session of the day and before the introduction of our expert speaker, I would like to set a little context here for our viewers, because we know we have the students from multiple streams. So just for them, I would like to share a few things. So I'm sure all of you are already aware of the term antibiotics, and we know they are known as miracle drugs. And the fact is that antibiotics are the one who have saved our lives from multiple infectious diseases, and they have also increased our life expectancy. So whenever we get sick, we are not worried. Why? Because we go to doctor, the doctor prescribes us antibiotic, and yes, we are fine after a couple of days or 3 days or 4 days. But the overuse, inappropriate use, and misuse of these antibiotics is increasing day by day. And it is making these pathogens, the disease causing organisms, more resistant toward the antibiotics. So just imagine a situation. You felt sick, you went to a doctor, but you felt sick because of a resistant pathogen. And even after the prescription of the doctor or the consumption of antibiotics, you are back to square one. You are still feeling sick and you are not normal. So just imagine that situation. I am sure it's very scary. And nowadays we are all are facing the problem of COVID-19. Yes, we know it came to us with surprise, but the fact is about these drug-resistant pathogens, we all are very well aware. The whole scientific community knows about it, that yes, this is something which is coming up and it is emerging on daily basis. So for that, scientific community is not sitting idle. The healthcare professionals, they are not sitting idle. They are doing something about it. And one of the options or one of the alternate ways to fight these drug-resistant pathogens is to come up with the alternate of antibiotics. And today's webinar is all about it. That is the use of botanicals for combating drug-resistant pathogens. So after attending this session, all of us will be able to understand and gain insights about the basics of antibiotics and antibiotic resistance. We all will be able to understand that how these botanicals, the plants, they can help us to fight against these drug-resistant pathogens. So allow me to share some technical details about today's webinar. This webinar is being conducted on Zoom and it has been streamed on YouTube. And I'm sure when you are listening to the expert talk, you always have many questions in your mind. So don't worry, we are giving you that chance. Please use the chat box in the YouTube and write hashtag Ask Prevented, and you can type in your questions. And I will ask the expert by the end of the session, and then she can just reply to your queries and questions, whatever you have in your mind. Now let's listen about the qualities or the experience of our expert speaker for the day, that is Dr. Tannaz Birdi. Right now, she is working as Deputy Director at the Foundation for Medical Research. And from her CV, I have taken 4-5 lines because it was very lengthy, but for keeping the time in mind, I just want to share the highlights from her CV. She did her basics degree in the field of microbiology, followed by the key interest in immunology. She is already guiding many PhD students, and she has many publications to her credit, that too in peer-reviewed international journals. She has been awarded the Major Journal Sahib Singh Sokhe Award from ICMR, that is Indian Council of Medical Research, based at Delhi. Currently, she is involved in exploring innovative holistic approach to use the medicinal plants in healthcare. And the fight against antibiotic resistance is one of her fields. So without much ado, I welcome Dr. Tannaz Birdi, and I would like to pay our regards and thanks to save and come and share her experience with all of us from her busy schedule. Over to you, Dr. Tannaz.
Good afternoon, everyone. So today what we are going to talk about is the use of medicinal plants for combating antibiotic-resistant infections. Next slide, please. Now, I think, next slide. Dr. Kaur has already mentioned. So why do we think that antibiotic resistance is a growing threat? Next slide, please. Let's look at some of the figures. There is resistance to most antibiotics is increasing. As you're aware, drugs like sulfonamides, tetracyclines, quinolones, all of them have bacteria have developed drug resistance to these. And the high rates of resistance are mainly towards antibiotics that are frequently used to treat common infections. For example, ciprofloxacin, a very widely used antibiotic. You will find that in different scenarios, the resistance of E. coli goes up to about 92% of the E. coli can be resistant to ciprofloxacin. Even Klebsiella pneumoniae. Now, both these two are airborne infections. And you will find that 79% of Klebsiella pneumoniae can be resistant to ciprofloxacin. The same thing goes for cephalosporins. 36% of E. coli can be resistant not to first and second generation, but even to the third generation cephalosporins. And methicillin, which is one of the most advanced drugs, even there you are finding 12% resistance developing from Staph aureus. Then if you come to other more serious infections like TB, there also you have about 500,000 TB patients having resistance to rifampicin. And about 3/4 of them are resistant to other drugs as well. And I'm sure you all have heard of superbugs. Now, these superbugs are those that are resistant to most antibiotics. Therefore, we are soon coming to a situation where we will not be able to use antibiotics to treat infections. And that is an alarming situation. Next slide, please. So what has been done about it? We have developed antibiotics against a wide range of bacterial targets. And these are all the targets. I'm not going to go through them. Next slide, please. So let's go. If man has developed antibiotics against all these targets, bacteria have not sat idle either. They have developed mechanisms by which to resist these antibiotics. So let's see some of the mechanisms by which bacteria can resist these antibiotics. First, of course, is spontaneous mutation. Now you will say, but spontaneous mutation is in the range of 10 to the -8 or 10 to the -9. Fine, that can be considered rare. But when a bacterium is fast growing, then that cuts the time span much faster. Then the next one is plasmids. Now these are DNA that are extra chromosomal. They lie in the cytoplasm. Now, if you, and what happens is a plasmid can have genes for multiple drugs. So they can code for multiple drug resistance. And it is much easier to spread drug resistance through plasmid-based mechanisms. Next slide, please. Yeah, another mechanism is inactivation of the antibiotic. Now, what do we mean by inactivation? The bacterium has enzymes that will either degrade or modify the antibiotic so that the drug or antibiotic becomes inactive. For example, with penicillin resistance, the bacterium, if it has beta-lactamase, it will degrade the antibiotic, and the bacterium will then not have to respond to the antibiotic because it's been degraded and inactivated. Another mechanism is target site modification. What we mean by that is that the bacterium changes its target. That means if the antibiotic is working against X target in the bacterium, the bacterium will modify its target or replace it so that the antibiotic cannot act on the bacterium. For example, in methicillin-resistant staph, what happens is there is a product called PDP, forget the name, which has a very low affinity for beta-lactams. Now, if that PDP is there, then beta-lactams cannot act on the staph. And therefore, all beta-lactams, which normally bound to this target, are ineffective, such as, and beta-lactams is a wide range of antibiotics, straight from cephalosporins right up to the carbapentins. The next method by which bacteria have eliminated the use of antibiotics is entry pods. That means it prevents the antibiotic from entering into the bacterium. There are pores or porins, as they are referred to, in the bacteria. And some drugs enter the bacteria through these porins. Now, if the purin is lost mutationally or altered, then the drug cannot enter and act. And this is the mechanism that is used by Pseudomonas to prevent imipenem from entering, therefore becoming resistant to imipenem. Now remember, imipenem is a drug of last resort. It is one of the major drugs that is available in man's armamentarium as for very severe infections. So even that has been breached by this loss of porins. The next method by which bacteria can prevent antibiotics from acting is efflux pumps. Now, these pumps are nothing but pumps that pump out the antibiotic. So if the antibiotic enters the bacterium, it is pumped out quickly. So you have 5 superfamilies of pumps, but that is unimportant for this. Just to remember that bacteria do have pumps that can throw out the antibiotics if they have entered. And the last method by which bacteria protect themselves is biofilm formation. Now, what is this? This is surface associated microbial communities which enclose themselves in a self-generated exopolysaccharide. Polysaccharide means carbohydrate matrix. So they form communities and they enclose themselves in this carbohydrate matrix, which prevents the drug from entering and therefore protecting it from preventing the antibiotic from acting. A common example is biofilm formation by Pseudomonas, especially in urinary tract infections. Next slide. So what has led to this rapid increase in AMR? The major reason is selective pressures which result in amplification. Now, what do I mean by selective pressures? Imagine you had, say, 9 out of 10, you had 9 sensitive bacteria and 1 resistant bacteria. Now, if that was the scenario as it would normally have been, then the 9 sensitive would have kept that 1 resistant at bay and controlled matters. But into this environment, you throw an antibiotic, which is your selective pressure. What happens? The 9 sensitive bacteria will die. That leaves only that 1 single resistant bacteria alive. And that resistant bacterium will have a field day. It will multiply constantly. Okay? So that is what is selective pressure. Now, how does that happen? You can have increased use of antibiotics, especially broad-based antibiotics. So what happens is the doctor says, oh, you have a cough and cold. He'll give you the highest generation of antibiotic, which works on all sorts of bacteria. So this broad spectrum antibiotics, while they are a boon, they are also a problem. Then you have incomplete treatment. You feel better after the first 2 doses, you stop treatment. Third, it's the antibiotics are at present sold without medical prescription or supervision. The next one is increased prophylactic use, especially before surgery. That means you think that you will get an infection, though you use prophylactic antibiotics. And one of the major problems is using antibiotics for viral infections. Now, antibiotics don't work on viruses. And yet, every time we get a cough and cold, we take an antibiotic. We don't even bother to think whether it's viral or not, bacterial. Then, of course, there are things like hospital spread of infection and antibiotics in animal feed and aquaculture. In fact, if you go through various databases, you will have see that there are about 20,000 potential resistant genes of nearly 400 different types available on the bacterial genome. And I don't have to tell you the impact of all this. There is treatment failure, longer recovery time, longer hospital stays, higher risk of mortality, long-term health implications, and of course, increase in cross-treatment. Next slide, please. Okay, so what are the difficulties in combating AMR? Obviously, one would say, okay, if the bug is becoming resistant to one antibiotic, we'll find another antibiotic to which it's sensitive. And this was the time of the 50s and up to the 70s, which was considered the golden era of antibiotics, when number of antibiotics were discovered and widely used. But as you come closer to the present day scenario, you find that between 2008 to 2017, only 2 new antibiotics were developed. And if you go a little bit back to 83 to 87, 16 were developed. So you can see that the era of antibiotic development is also fast coming to an end. And that is why WHO has declared AMR one of the biggest threats to global health. Okay, so there is an absolute urgent need for developing alternatives. Next slide, please. Now, what could be these alternatives? How do we mitigate AMR? First, there is the public health approach. And second, there is a more research-based and lab-based approach. So first, let's look at the simple public, not simple, but the doable public health approaches. What is the importance of that? There is you use these approaches to reduce the need and unintentional exposure to antibiotics. So how would you reduce the need and unintentional exposure? One is hygiene and sanitation. All of you know that if you have good hygiene and good sanitation, you're less likely to get infections. Secondly, similarly for animals, if you have good animal husbandry, then the use of antibiotics to treat poultry and animals is decreased. Then you should decrease the use of antimicrobials in pesticides as pesticides for crops. Obviously, treatment of hospital waste is important. Then one has to regulate antibiotic emission into the environment. Pharmaceutical industries which produce antibiotics must ensure that these antibiotics are not leached into the environment, either through water or air, or into the soil. The other thing is that India, at least, does not have a buyback policy for expired or unused antibiotics. So what do? We buy a strip, we may use half of it, the second half goes into the dustbin, which goes into a recycling plant. So in that way, the antibiotic goes into the environment. And of course, one should optimize wastewater treatment plants, so that they do more than just remove the fecal coliforms. And the other ways of removing the antibiotics is optimized use of antibiotics. That means you can remember, if you use more than one antibiotic, the bacterium has to have both the or multiple methods of dealing with those antibiotics. So the chances of mutations is less. It may develop resistance to one antibiotic, but it would be killed by the second. If it develops resistance to two, it may be killed by the third. So that is the concept of multi-drug resistant or multi-drug treatment. The other thing is that has been used in other countries. It hasn't come into India, partly because you need the system is recycling of drugs. That means you have good supervision, and you find that if one drug, if the country is becoming resistant to one drug, you withhold that drug. So the bacteria getting resistant to drug A, you take it out of circulation. You put B inside. Then once the people are becoming resistant, or the bacteria are becoming resistant to B, and you see that the A resistance is decreasing, you bring back A. So that way you increase the life of the antibiotic. And lastly, of course, you have to invest in development and access. It's not just development, it is also access to diagnostics and new therapies. If you develop a new therapy or diagnostic which is not easily accessible, or the technology is so complicated that it cannot be used, or it is too expensive for use, then it is of not much consequence. So we come to what are the alternatives to conventional antibiotics? What is presently available or is in the research stage? The first is probiotics. Now, as we and the resistant one has a field day. Now, if you give, in this scenario, probiotics, which will counter the one resistant bacterium, it will keep that resistant bacterium at bay. So that is the principle of probiotics. Then you have bacteriophages. For those of you who don't know, bacteriophages are viruses of bacteria. Just as we have viruses for humans and animals, in fact, COVID is a classic example, you have viruses of bacteria. Now, what these phages do, and they're referred to as phages, what these phages do is they get into the bacterium and they kill the bacterium. So you have treatment with bacteriophages. This is of limited use at present and can be only applied to surface infections. Then you have antimicrobial peptides of eukaryotes. Now, antimicrobial peptides of eukaryotes, what are they? Now, these peptides were the early forms of defense that were used by eukaryotes. And they are able to kill the bacteria, such as defensins, lysins. But these are still limited use or still in the research stage. Then you have antibodies that are used. Now, you've all heard of people asking for convalescent COVID blood donation. What is that? That means the antibodies that were present in an individual who got COVID, those antibodies could be given to another person for recovery from the infection. And history takes us back earlier, where convalescent plasma was used to treat. But that is third stage is the oligonucleotides for silencing resistant genes. You may have heard of the term CRISPR, which is a recently developed technology which is used for this purpose. And finally, perhaps what is the most easily accessible and the most easily developable is the use of medicinal plant extracts. And we will go into that a little bit more now. Next slide, please. So we have seen that man has developed antibiotics, bacteria have developed mechanisms for dealing with those antibiotics. And what have plants done? Plants have also not sat quiet. They have produced a wide range of compounds which may not be important for their primary metabolism, but signify an adaptive capability to adverse environmental conditions. These compounds are often referred to as secondary metabolites, which have evolved so that they act as a defense mechanism against the environmental pathogens, plant pathogens. And we will go into that a little bit more in detail later. Antibiotics have been isolated from botanicals, and the most recent is artemisinin. But so just up to this point, just to summarize, antibiotics work on the principle of one compound, one target, and therefore development of resistance is easier. And what I want you to hold in your minds is that plant extracts have multiple compounds with different targets, making resistance generation difficult. And we will discuss that and see that a little bit more in detail as we go further. So first, let's look at the plant secondary metabolites that I just talked about. I don't want you to go through the details of it, but I just want to emphasize and impress upon you through the next few slides the structural diversity that exists in these secondary metabolites and the vast array of compounds at our disposal within these secondary metabolites. In fact, there are 7 groups of compounds that consist of together make up these secondary metabolites. The first is alkaloids. And the second is terpenes. Now, terpenes themselves is the largest group, and there are 30,000 known structures. Essential oils forms a part of this group. Next slide. Then you come to the phenolics or the polyphenols. Now, this is a very diverse group of compounds involved in plant defense. And within that group, you have flavonoids and quinones. Next one. Tannins. Now, tannins are present in almost all plant parts, and they are widely available, and you have different types of tannins, but we will not go into that at this point in time. You then have coumarins, which are also more often produced when the plant is trying to fight a microbial infection. So it's a self-defense mechanism. Then you have lectins, again a diverse group, which act by preventing adherence of the microbe to the host polysaccharide. So it's a competitive method by which these lectins work. They prevent adherence of the microbe to the host polysaccharide. And of course, it can it's involved in the formation of ion channels, and it has versatile antibacterial and antifungal activities. And lastly, you have the saponins. Now, saponins, you can correlate with soap. That means they lather, they have a lathering capacity. And many of the Chinese herbs are very rich in saponins, such as licorice, ginseng, etc. So on the whole, there are 7 different classes of secondary metabolites. Now, how do these secondary metabolites work in preventing or combating resistance to antibiotics? You all know that the easiest way to check is to see whether the antibiotic-resistant bacterium is killed by the so-called plant extract. Now, that is the simplest way of doing it, and it does do that in many cases. However, in other cases, it may not kill the bacterium, but it may attenuate bacterial virulence. That means it prevents the bacteria from either entering or becoming pathogenic. For example, cypress and bael. Both these two prevent bacteria from colonizing the gut. And therefore, while they don't kill the bacterium, if the gut is not colonized by the bacteria, it gets flushed out. So this is what I mean by attenuating bacterial virulence. Another example is bacterial hemagglutination. Then we come to inhibition of biofilm formation. Simple things like lemongrass, cloves, cinnamon, and in fact, one of the most potent inhibitors of biofilm is neem. These inhibit these microbial colonies from forming. And therefore, if the colony doesn't form and that polysaccharide or carbohydrate matrix is not formed, then the drug can penetrate and kill the bacteria. We've talked about efflux pumps. Those are pumps that throw out in the bacteria that throw out the antibiotic. Now you have inhibitors of those efflux pumps present in a number of plants, such as rosemary or pepper. Next slide, please. Then you come to a more general mechanism, which is immunomodulation. It means that the body's own immune mechanism is stimulated to kill the pathogen. And there we have two types of immunities. One is the innate immunity, and the second is the acquired. Now, in innate immunity, it is, for those of you who are not familiar, it is non-specific. And it's the first line of defense. So, for example, a phagocyte or say a macrophage will engulf the bacterium and kill it after getting activated. So you can check for enhanced intracellular killing. You can check for increased phagocytosis. You can check for increased, now the others are IL-1 and TNF-alpha are cytokines that are secreted by the cells. So increased IL-1 secretion, increased TNF-alpha secretion, and then once the bacteria is within the cell, it gets killed by NO, nitrous oxide, or reactive oxygen intermediates. So all these, both these two together, kill the organism once it's engulfed. So all these are methods whereby if you stimulate the cells, they will kill the pathogen irregardless of whether it's antibiotic resistant or not. Next slide. Then we come to acquired immunity. Now, acquired immunity is where you have a degree of memory, in the sense the immune mechanism has to see the host, and it's far more specific than the innate immunity. And here we have two types of immunity. One is antibody, and the other is cell-mediated. So for antibody stimulation, you have a number of plants that work. One is herde, the other is ginseng. So both these two stimulate antibody response. When you come to T-cell mediated response, you have this mushroom, which stimulates gamma interferon secretion. And this is just one example. And then you have Panax ginseng and Embolica officinalis, both of which stimulate both humoral as well as cell-mediated immune responses. So there are some plants that will stimulate both types of immunity, and some plants which are selective in what they stimulate. Next slide, please. Yeah, and perhaps the most important aspect of medicinal plants in treating infections is the property of synergism and additive effect. Now, when we talk about synergism, it means that the combined effect is greater than the sum of the individual components. And additive is just the combined effect is equal to the sum of the individual components. Now, remember, when you talk about a plant extract, it has a number of compounds in it. We've seen how many compounds when we saw the secondary metabolites. There are thousands of compounds in a plant. So may not be all, but at least a fair proportion of them will be in any one extract. So if you're talking about extracts, they contain numerous compounds. And often there is synergism or additive effect. Now, let me give you an example of something that I've worked with closely. We've looked at the guava for its antidiarrheal activity. Now, the guava leaf extract does not kill the E. coli that cause diarrhea or the different types of E. coli that cause diarrhea. But what it does is it prevents adherence of the bacteria to the gut. It prevents invasion of the bacteria to the gut, into the gut. It prevents toxin production. And even if toxin is produced, it prevents its binding. It also prevents the anti-inflammatory cytokines from being produced. So it has a wide array of activities. Now, this is not from one compound in the extract. There are multiple compounds in the extract that combine together to finally give you the end product. And therefore, often what happens is in industry where they want to standardize or they want to produce it, what they do is they do isolation of the activity. Now, when you look for isolation often leads to loss or reduction of activity. So there is, for example, if you see tamarind, when it was fractionated against Pseudomonas, the extract lost its activity. And the same goes for most other extracts as well. The activity is significantly decreased or lost when you try to isolate the active compound. Because remember, as I told you earlier, it is not a single compound that works in an extract. It's synergism or additive effect. And therefore, the principle of antibiotics working one compound, one target. Medicinal plant extracts, multiple compounds, multiple targets. So it's easier for drug resistance to develop for compounds with one activity, one target, versus plant extracts which have multiple compounds, multiple targets. Next slide, please. Then there is another kind of interplay that can take place. That is bioenhancers. Now, bioenhancers will either improve the uptake or absorption and therefore the activity of antibiotics. They are not therapeutic in themselves, but they will improve the functioning of the antibiotic. How does it do that? It increases drug absorption. It modulates biotransformation through the liver or the intestine. It modulates active transport, or it decreases elimination. Next slide, please. And there are some examples. The fact that there is a fourfold reduction in the MIC of tetracycline and erythromycin when you combine these antibiotics with mango extract. Secondly, if you combine methicillin or beta-lactam antibiotics with berberine, then it acts on MRSA. Piperine, which is pepper, increases the bioavailability of rifampicin for TB. In fact, it decreases the dose required from 450 milligrams to 200 milligrams. Then turmeric increases the bioavailability of other antibiotics. So in general, bioenhancers are very useful for antibiotics which are still active, but at a higher MIC value, which may be toxic to the patient. Next slide, please. So let's just recap what we've come. The key points. One is that plants have been used over centuries and identified through traditional knowledge, and they are still effective. There is no drug resistance to them. And that is because of the structural diversity of the phytochemicals. Then there are numerous constituents of plant extracts having multiplicity of targets. I've stressed that over and over again, the importance of additive and synergistic effect. And therefore, the chances of developing bacterial resistance to these extracts is much less. Next slide, please. So then why are we still not using them more widely? What are the reasons for that? Even though we have such a wide knowledge and such an extensive source of anti-infectives. In fact, if you were to study these from traditional knowledge, you would have a higher proportion of positive hits, as pharma industry calls it, and which would be far more cost effective. But what are the problems? One is standardization is difficult because often there is no one single active principle, or the is unknown. Secondly, as I told you again, synergy of two or more compounds is important. And so, but what has industry done usually? They usually standardize extracts on the basis of the presence of marker compounds. Now, these marker compounds may be present, but because of the variation in the environment, the biological activity may vary because of the quantity of the unknown active principle. And therefore, standardization becomes very difficult or challenging. Thirdly, patenting of herbal products is not always possible. And therefore, there is lack of investment by industry. And what is the implication of lack of investment by industry? That the extensive pharmacopoeia that we have remains underutilized. There is lack of in-depth research into development of herbal medicines. And thirdly, it results in labeling of products as food supplements to shortcut the process. Now, not all these products are food supplements. These can be made into medicines. Therefore, my last message is, a modus operandi needs to be worked out wherein both industry and the traditional knowledge sector, both codified and not codified. Codified means Ayurveda, Chinese medicine, Unani medicine, and non-codified is what is transmitted from generation to generation, or what is commonly known as folk medicine. Both these two methods need to be integrated to come together and to develop better medicinal plant products. Thank you very much. And this is just one of the references that you can look at, which summarizes a large proportion of what I have discussed, if not all. Thank you.
Thank you very much, Dr. Birdi. It was a very informative talk, and you have used a very simple language. I hope all the audience must have gained a lot from this lecture. We have got 5-6 questions, but keeping time in mind, I will just take 3 of them. So first question is, what is the current stage of these plant extracts? Like how far we have reached?
See, you will find that in Ayurvedics are using the plant extracts. But again, there are Ayurvedic companies as well, which do produce quite a few of them. So it is there, but it's just as you go to an allopath or you go to an Ayurvedic physician, you need to make it more popular, especially for the use of antibiotic-resistant infections. Mostly Ayurveds are approached when there is a chronic disease, not an infectious disease. Because we still believe vastly in our research into antibiotics. And true, we have been in an era where we could just pop a pill and get cured. But whether that will continue is to be questioned. So you do need a great deal of talk and development to cross talk to get these medicinal plants into formulations to make them into standard products.
In continuation of this question, another question is that normally a vaccine or any antibiotic product take many years to come into market. So if we talk about any botanical product, so how much time does it take from a lab to come to market?
Yes, I think quite a few would have heard of Dr. Ashok Vaidya's terminology, reverse pharmacology.
Yeah.
Now, what is reverse pharmacology? You take traditional knowledge and you take it back into a formulation. But let me, it's a good question in the sense that I would like to bring out certain bits of information here. One is that there is a lot of published papers on ethnobotanical surveys. And what do these ethnobotanical surveys mention? They tell you the plant. At the best, they will tell you what part and what it acts against. Very few of them will tell you how to prepare that plant product extract. Is it to be prepared in oil?
Yeah.
Is it to be prepared in as a decoction, as an infusion? That is very rarely done. So one has to understand how it is. For example, Karanj, which we have worked with. Now that is a plant that if you just take it constantly, it has CNS toxicity. But the locals know that you cannot take it regularly. They know that you must take it only once, only one leaf once. So you have to bear in mind the traditional knowledge and the traditional use. So while we may refer to these surveys, you have to bear in mind that there is a lot more behind that.
Okay. Yeah. The next question is that how much our government is giving importance to these botanicals? Because
you all know that Ayush is,
yeah, it's into.
But that is again, they are trying to promote it, but there's much scope for improvement.
So the last question.
And consensus between the Western medicine and the Ayurveds. They must come together and work together. That is crucial.
Yeah. So coming towards the last question, I think you have already covered about this during your talk, but if you would like to add any point to this question, somebody has asked that you discussed about the other alternate therapies like CRISPRs, bacteriophages, and medicinal plants. Obviously, you talked in details. So out of these, which one you think is the best one, like which have more scope?
I think each one, including medicinal plant, has its niche. Okay. Now, if you were to be a great promoter of Ayurveda, and you would still have, if you had a surgery to be done, you would still go to a Western medicine practitioner.
Yeah.
So each discipline of medicine, each technique has its niche. Bacteriophages, fine, very good, but they cannot be taken as internally. So they have a niche, it's for surface. So each approach has its niche.
Yeah. Okay. So on that note, I would like to thank Dr. Birdi, and on behalf of all the listeners and my team, that you agreed to share this valuable information with us. Any message you would like to share with our viewers from your side?
No, just to say a big thank you. And if you want further details, you're welcome to email.
Sure. So, so listeners, we have.
Would like to sort of work on this, then we can always talk.
Sure. So during my presentation, I had shared one link of FMR, which is the official website for wherein Dr. Tannaz Birdi is working. And so we have come to the end of the session. So I have already paid my regards to Dr. Birdi for her valuable time and very fruitful information she had shared with us. And I'm on behalf of our team, I would like to apologize if anybody has faced any technical problems, but still, if you have missed this session at this point of time, you can always go back and log into our preventive page, LinkedIn, Facebook page, and Twitter page, and utilize this information for future search. And yeah, that's all from our side. Stay healthy and stay positive. Thank you, Dr. Birdi, and bye-bye from our side. Thanks.